Okay, so good afternoon again. So if you didn't complete today the course evaluation, it's very important not only for this course, for all the course that you are enrolled to complete the course evaluations. So the URL and the link is on this slide. You can click on it and you can access the course evaluation using your passport, username and password. Now, we start our lectures by reviewing some topics about the previous lecture we discussed. We discussed the quick sort, recursive algorithm for sorting an array. And we saw that the quick sort is using the methodology of divide and conquer. We divide the array and we try to sort each part of the array. And we keep dividing the array until we have one element. If we have an array of size 1 element, this array is sorted. That is the base case. Then we do the collect the sorting array. Then we discuss the difference between the recursion algorithms and iteration algorithms, or you can say an recursion algorithm or approach to solve the problem and iterative approach to solve the problem. And we look at the implementations of Fibonacci numbers indeed. And we saw that using the standard implementation for the Fibonacci number for the recursions, we are calculating the same problem twice, or maybe more than that. So we revise the implementation so we can end up with time complexity order of n. And we close the last lectures by analyzing the recursive algorithms. Today we will continue discussing analyzing the recursive algorithms and how we can start from Java implementation for a recursive method and extract the recurrence relation. And from the recurrence relations, we expand it to find the time complexity of any particular recursive algorithms. Also, I brought today some previous examples from previous years. So students are given an API for a recursive methods, and we ask them to implement it. And we have some examples we will discuss today. And I would like you to look at this example and see how the other students, when they read the API, approach the problem. Also, we look at how we can prove the correctness of any recursive algorithm. So if a recursive algorithm is given to you, and someone asks you if this recursive algorithm is correct and can be terminated successfully or not, you can test that. And to prove that the recursive algorithm is correct, we're going to use the proof by inductions. So proof by inductions, a topic you covered already on the previous course. A prerequisite for this is discrete math. So we're going to use the proof by inductions to prove the correctness of a recursive algorithms. Starting from analyzing nested loop, we discussed this last time. So you can see here we have two for loops. They are nested. The first loop is start from I is equal to 1 up to n. And the second loop, which is depend on the outer loop, where j is equal to I up to n. Then we have one statement, sum equal to sum plus 1. Now, based on the analyzation of and our assumption that each statement will run using 1 unit of time, we can analyze and extract the time complexity of this two nested for loop. We can start by using two double summations. So you have two double summation. The outer summation start from I is equal to 1 up to n. The inner summation is start from j is equal to I up to n. Now, 1 here represents the time complexity for running this statement. Sum is equal to sum plus 1. So we have one statement, and the running time for this one statement is 1 unit of time. Now, if you see that the argument inside the summation is independent from the indices, so we can take the upper limit minus the lower limit, so n minus I plus 1. Now we can expand the summation to distribute it over the n plus 1 and minus I. Now again, you can see this quantity. We can end up with the summation n times n plus 1 minus n over n plus 1 over 2, which is n times n plus 1 over 2 equal approximately n squared. So the time complexity for this two nested loop for loop is n squared. This is a detailed analysis for these two for loops. You can see in the implementation here, the nested for loop is j is equal to I. Because that is what we design, how the implementation. We analyze this. If you want to change the problem, you want to say for j is equal to 1, then you will have different argument here on the summations. Okay? You are given this 4 lines of code, and we ask you what is the time complexity for this two nested for loop. Now, if you want to say if j is start from 1, not from I, you start talking about different problem. Okay? Okay? Now, if we need now to take this background analysis for the nested for loops, and we need to discuss how we can analyze and extract the recurrence relations from recursive algorithms. We start by defining that any recurrence algorithm relations start by saying T of n. You can name it W of n, but we use T capital to stand for time. And in here, we have an integer variable that represents the size of the problem that you are trying to solve. So here is T of n represent the recurrence relations. And for any recursive algorithms, you will have the base case and the recursive call. And again, this is the same thing on the recurrence relations. We have the base case and we have the recurrence relations. As you can see here, this T of n is, if n is equal to 1, we have A, the solution for this recurrence problem. So if n is equal to 1, we have the immediate solution is equal to A. Now, if n is greater than 1, in this case, we're going to use 2 times T of n divided by 2 plus P of n plus C. You can see the time complexity that's depend on n. We can write it in terms of n over 2. So to calculate, for example, T of n is equal to 4, where n in this case is greater than 1, we're going to substitute. T of n is equal to 4 is equal to 2 times n is equal to 4 divided by 2, which is 2, plus P of 4 plus C. This is a recurrence relations. And as you can see, there is a recurrence problem or recursive relation that depend on the futures, and there is a recursive problem that depend on the past. Most of the discussions for this lectures or for this course, we're going to discuss the recursive relations that depend on the past. So we start from n large and we rely on the time complexity for small n. In this case, n is equal to n, and we write it in terms of n divided by 2, or even in terms of n. Now, any recurrence relations, it has similarity with the recursive algorithms. We have the base case. In this case, if n is equal to 1, and we have recurrence relation when n is greater than 1. And the constant A, P, and C, they are not important for us. They are important if you would like to find the exact solution for a recurrence relation. But for our course, A, P, and C are not important for us because we are trying to find the time complexity in terms of big O. Let us see how we can formulate the recurrence relations given the Java implementation. So this example here, we have public void function f that's take argument integer is equal to n. And we check if n is greater than 0, we're going to print n. Otherwise, we're going to call for f of n minus 1. You can see here the base case is there. If n is start being negative, so we're not going to do the recursive call. And if n is greater than 0, we're going to do the recursive call for n minus 1. So starting from this example, we start by saying that if n is equal to 0, then we have T of 0. N is equal to 0, and this will give us a constant amount of time to solve this recursive algorithm. So if n is equal to 0, you have a constant time. There's no recursive call. The solution is immediately available. So we have a constant of time to solve the problem, and that we indicated by a. So t of 0 is equal to a. Now, if n is greater than 0, then we're going to do the recursive call. But there's some if statement. We're going to check if n is greater than 0. We're going to print, and then we're going to do the recursive call. The recursive call needs to store some frame on the stacks, and you need to store all the local variables and where is the point you have to retain. So there is some time you need to spend while you are doing the recursive call. But now look at the size of the parameter. We start from n and we call for n minus 1. So the recursive call, if the time complexity to solve the problem for t of n will be equal to p, which is the time, constant amount of time to do the recursive call to store the frame on the stack and all the local variables, and plus the time complexity to solve the size of the problem n minus 1. So how much the time complexity for n minus 1? I have to do the recursive relation again for the time complexity for n minus 2. So now you can see here the time complexity for t of 0, where the size of the problem is equal to 0, is a constant time, which is matched with the recursive methods. If we have the base case, we reach the base case, immediately we have the solutions. We don't need to do the recursive call. But if we have n, then is equal to p, a constant time to do the recursive call, divide the problem from n up to n minus 1, and then with the time complexity for n minus 1, the time complexity to solve the smaller size of the problem. Yes. You can change it to have n is equal to 0 or n is greater than 0. You will not change the analysis of the time complexity. Okay? It will change the where you're going to stop. If you say n is equal to 0, then you lose one iteration. If you say n is greater than 0, because 0 is not greater than 0. 0 is equal to 0. You're going to lose one iteration. That is all in terms of the solution. But in terms of analysis of time complexity, will not make any difference. Okay, if you have given any recursive algorithms, you will start asking questions, how I can formulate the time complexity. T of n is equal to, if the base case is reached, then you have some constant amount of time to solve the problem. You don't need the recursive call. Else, that means we are not reaching the immediate solutions. We have to then consider the time to divide the problem into sub-problems, plus the time to combine the solution of these sub-problems. To be able to do this, we're going to ask 3 questions whenever we are trying to analyze any recursive algorithms. How many sub-problems we have if we start with n, size of the problem, and we, at each recursive call, how much or how many sub-problems we have. How much smaller are the size of the problem when we divide it. For example, if you consider a binary search, you start with a sorted array. You start with an array of size n. Then at each iteration, you start dividing the array of n over 2. So if you start with n, the size of the smaller problem is n over 2. How costly to combine the solutions? If you saw in the merge sort, you divide the array into halves. The decompositions of n to n over 2, n over 4, n over 8, n over 16 until you have one element. Then there's a time complexity to merge all these sub-problems together, which is order of n, because you have to merge these 2 sub-arrays sorted. Now, to solve any recursive relations, we're going to use these iterative methods. There is a lot in the literatures. There's many other methods to solve any recurrence relations. But for this course, we're going to take the iterative methods and we're going to use it to solve any recurrence relations. The steps for this iterative approach is expand the recurrence relations, express the expansion as a summations by plug in the recurrence back into itself until you see the pattern. Then evaluate the summations. How we can take these steps into an examples? Here we have examples where we have to sum the values inside the queue. We ask if the length of the queue is equal to 0, we're going to retain 0. That means this is the base case. I give you the queue and I ask you sum all the elements inside this queue. Then if we're not reaching the base case, that means the queue, the size or the length of the queue is not equal to 0, then we're going to do the recursive call. We're going to retain the queue.dq. That means we're going to take the first element of the queue, and then we're going to do the recursive call. We're going to call the same method again, sum of the queue. But now, if you notice here, the queue.dq will reduce the size or the length of the queue. If you start with the length n, queue.dq will make it n minus 1. And when you call it here with a queue, that means this size will be reduced by 1 until you reach the queue.length is equal to 0. So this Java code is start with dividing into one subproblem. As you can see, we don't have two subproblems because we just take first element of the queue, then we call for the queue of size of n minus 1. We decrease the size only by 1. Then we have some constant time to do the addition, okay? And one constant time times the time to solve the subproblems. So the equation or the recurrence relation will end up with t of 0 less than or equal to p, that the time complexity to solve or to sum a queue of size 0 is less than or equal to constant time. Now, if you want to calculate the time or complexity to sum a queue of size n, it will be less than or equal to c plus the time complexity to sum a queue of size n minus 1, as for all n is greater than 0. Any question about this? Yes. This equation, t of n less than or equal c, the time complexity to do the addition. See, these are constant, okay? And p is different. The value for constant p is different from the value for constant c in the real life, okay? Because the value for p is actually the retained 0, which is the immediate solution. You don't need to do any recursive call. But the time here, c, we indicated different. We're not using the same notation because it's different. Because you have to do addition, you have to do the recursive call, you have to store some frame on the stacks. Okay, so the time complexity for value, the actual value for p and c is different. But in our calculation, to find the time complexity, it will not affect us. Okay, because we are trying to find the time complexity in terms of big O notation. Okay, but if you are doing it mathematically, value for p and c, it's matter for you to find the exact solution for any recurrence relation. Okay, so now we have the recurrence relation. We extracted from the Java program. We have the recurrence relation. What we should do with it to find the time complexity for these algorithms. So we do the iterative approach. Iterative approach, we expand the recurrence relations and we substitute it inside itself. So you can see here the time complexity for n minus 1 is equal to c plus time complexity for n minus 2. N minus 2 is equal to c times n minus 3. Keep substituting until you see the pattern. The pattern here is k times c plus time complexity for n minus k. Now, for all k, now to find the exact solution, or not exact solution, to find the time complexity, let us assume k is equal to n. If we reach k is equal to n, in this case we have n times c plus time complexity for solving n is equal to 0, which is the base case scenario. In this case, the time complexity for 0, we know it is less than or equal to p, so we substituted, as you can see, the time complexity to sum the queue of size n is less than or equal c times n, which is the length of that queue plus constant. So if in terms of the big notations or big O notation, this is order of n. So this recursive algorithm, the time complexity of it is order of n, which is the linear time complexity. Any question? This assuming that this is the upper limit, because when we do the time complexity, we try to find the upper limit of the time complexity. That's why we use inequality here. That's less than or equal. Okay? That is why we are using less than or equal. Okay? Yes? P is not equal to C. P and C are constant. Okay? P and C are constant. They are not equal. But as you can see, whatever the value for C, whatever is the value for P, you pick it up, 10 or 100 or 1000, this time complexity for this algorithm will be order of n. T0 is less than or equal to P. P is a constant amount of time. P here is not a recursive relation. P is just a constant, any value, just a constant. To do the retain, to run any statement, let's say if you want to run a statement A plus P is equal to C, you need an amount of time from the CPU to run this statement. Let's indicate this amount of time to be equal to P. Okay? C here is another constant. Okay? Any other questions? Okay. Now let us see the binary search. If you remember the binary search, we discussed that we start with recursive algorithms to divide the array of n onto n over 2. So here is the recursive relations. So T of 1 is less than or equal to P. P is a constant amount of time. So if you have array of size 1 element and you would like to do the binary search, you will have a constant amount of time to solve this problem. The only thing, you're going to see the target and you compare it with only one element. So it's only if statement. If the target is equal to this element, then retain it true or retain the index what is that element is, because the size of the array is only one element. Now, if the size of the array is n, at each iteration or at each recursive call, you start with n. You're going to compare the target with the middle. If the middle is greater than, or the target is greater than the middle, you're going to look at the upper half of the array. In this case, you reduce the array size n over 2. By reducing the size n over 2 at each recursive call, so the time complexity to solve the problem of n is less than or equal to the time complexity for solving n over 2, plus another constant c, which is the constant to do the comparisons, to copy the array, the upper half or the lower half. All these process has a constant amount of time, is not related to the size of the array. Having these recurrence relations, to solve these recurrence relations, we're going to use the iterative approach. We're going to try to substitute, expand these recurrence relations, and substitute inside itself until we see the pattern. So let us start here. The time complexity to solve the problem for n is less than or equal to n over 2 plus c. Now we substitute the time complexity for n over 2 is equal to time complexity n divided by 4 plus c plus c. Then n over 8. Did you see the pattern here? The pattern is n divided by 2 to the power k plus kc. Now, we are using in this one is t of n over 2 is less than or equal to t of n divided by 4 plus c. In this step, you can, to reach the base case, we're going to have n divided by 2 to the power k is equal to 1. That is the base case. To be able to solve this, we're going to rely on the initial condition. If you want to say it, is the base case where the initial condition is given to us. What is the initial condition? Is t of 1 is equal to p or less than or equal to p. Did you understand this? Perfect. Now what we do is, this is a recursive relations. We try to solve it. Okay? We try to solve the recursive relations using the iterative approach. So the first step is expanding this recurrence relations. To expand this recurrence relations, we substitute time for n over divided by 2 will be equal to what? Less than or equal to what? N divided by 4 plus c. So we substitute it back again. What is the time complexity to solve the problem of size n divided by 4? Is the time complexity to solve the problem of n over 8 plus c. We put it back inside the relation. So we end up with this formula. You see here, n divided by 2 to the power k plus kc. We can stop here. We need to solve it. The only thing is given to us is the initial condition. What is the initial condition is? T of 1 is less than or equal to p. So if we assume, and if you remember on the previous analysis, we assume, we say, without losing any generality, we assume that n is a power of 2. And we do substitution to end up with the formula of time complexity. Here it's become maybe more clear for you. To make this argument, n divided by 2 to the power k is equal to 1, to be able to substitute it, because we have the initial condition here. We know the time complexity to solve a problem of n is equal to 1, which is less than or equal to p. So if we take this argument, n divided by 2 to the power k is equal to 1, that's give you what? N is equal to what? 2 to the power k. Do the substitution inside, you will end up with time complexity for this recursive relations is less than or equal to p plus c times log of n. Because k is equal to what? Log of n base 2. Yes, log of n base 2. Yeah, because we discussed this on the time complexity. Whenever we use the log, we mean by log base 2. Okay? So now, if you have the solution for this recurrence relations is less than or equal to p plus constant times log of n. So what's the time complexity of this, or what is the, this belong to which family of time complexity belong to? Logarithmic approach. So the time complexity for the binary search is logarithmic approach. This is how we really mathematically prove it, that the time complexity for the binary search is order of log n. Any other questions? So now let us see another example we discussed on the past. We discussed the merge sort. We saw that the merge sort is try to take the array and end up with a sorted array. So the input is unsorted array, and we end up as an output of sorted array. To do this, we have to do the recursive call. We divide the problem into halves. So that means we end up always in two subproblems, not only one subproblem, two subproblems. We take the array, we divide it into the first half, the second half, or the lower bottoms, or the upper bottoms, I mean the lower part and the upper part. Okay? So take the lower part and also divide it into halves. Then you have to do some constant amount of time to sort these two halves. To do this, we have the recursive relation as if the time, if n is equal to 1, if the array of size n is equal to 1, then there is a constant amount of time to sort this array. If you have an array of size n is equal to 1, then the time to sort it is only constant amount of time, less than or equal to p. If you have an array of size n, then you need to divide it in two halves, n over 2, n over 2. So the time complexity to solve the problem of n will be the time complexity to solve two subproblems, n over 2. That's why we have 2 times n over 2. plus the second term here is to merge the two halves after you sort them. You have already divided the problem from n into n over 2. So you have two subproblems. The size of each two subproblems is n over 2. So that's why you have 2 times the time complexity for n over 2. Now you have two arrays. Imagine these two arrays are sorted, and you would like to merge them to end up with one array. What is the time complexity for that? Is n. You have to go over all the elements and do the comparison between all the elements to find out the sorted array. So if you have, let's say, you have an array of 2 elements, and you have another array of 2 elements, and you would like to arrange them. They are already sorted. How many comparisons you need? You need 4 comparisons, which is size of n. That's why we have here the term C of n, which is the time to merge the solutions. If you remember in the previous slide, we say if we don't have the base case, then we have to ask how many subproblems we have. In this scenario, we have 2 subproblems. And how much the size of each subproblem. In this case, we have the size of each subproblem is n over 2. To merge them together, we need n. So this term here is related to the merge the 2 solutions together. C is a constant. N is the time to merge because you need n comparisons. Okay? We use constant to make sure that we have a general recursive relations. Okay? But 2 here, we cannot change it to C or D. 2 is 2 because we have start with n, one problem, we divide it in 2 subproblems. We cannot change 2 here to put it, let's say, W or D, because 2 is 2 subproblems. Yes, but we focus only on one of them. We focus on one of them, we don't look at that because we compare the target. If the target is greater than the middle, we take the upper half and we start to look in that upper half. We forget totally about the lower half. But in the merge sort, no. We divide in 2 and we have to make sure that the 2 halves are sorted. Then at the last step, we have to merge them together. So to solve this, again, we're going to use the iterative approach. As you can see, the time complexity to solve for n is less than or equal to time complexity to n divided by 2 plus c. And now we keep substituting inside until we see the pattern. So if you keep substituting, you will see the pattern that the time complexity for n is equal to less than or equal to 2 to the power k time complexity of n divided by 2 to the power k plus k or times c of n. Now, to get rid of this argument, we look at the initial condition. We start the same thing. If we take n divided by 2 to the power k is equal to 1, then we end up with time complexity is n log of n, which is really the match our analysis on the previous lectures about the merge sort, that the time complexity of the merge sort is n log n, linear logarithmic time complexity. Yes, we are considering the upper part. Any other questions? Okay. So I hope now if I give you the recurrence relations, you can expand it. You can find the time complexity of any given recursive method. If you want to, yes, here is you have to, we discuss on this lecture is about time complexity, not the space complexity. So we only consider the time complexity for the algorithm. So to say that the implementation A is faster than implementation P, you need some standard, okay, some protocol or standard method that everybody going to look at it. So the big O notation is a standard method to compare between 2 implementation in terms of the time complexity. Now, if you write 100 codes and the other students write 2 codes and you end up with order of n, line logarithmic, and he is order with 2 to the power n, which is exponential, yes, your implementation is faster than his implementations. Now, There's sometimes people are take trade-off between the space complexity and time complexity, but the time complexity is one of the things that we are focused on in this course. Okay, we're not saying that if the number of code in your implementation is less than his number of implementation, that is related to the code style, and you get credit for using less number of codes. But for correctness, that is the one of the most important thing, that even if you are running fast and you produce a wrong result, will not help. The correctness of the implementation is one of the things that also we need to look at it, not only the time. Okay? Yes. We look at the quick sort in the previous lectures, and we discussed the normal scenario for the quick sort was n log of n, but the worst case for the quick sort was n squared. Okay, so here is we discussed the recursive algorithm, and we consider, let's say, you want to say the worst case, but sometimes we need to make some assumptions before we start our analysis. So like when we did in the quick sort, we assumed that the array is random. In the normal case, we end up with n log of n. But if the array is sorted and we try to run the quick sort, we end up with time complexity, square time complexity, quadratic time complexity, n squared. So what is assumption is given to you at the beginning of doing the analysis, okay? But most of the time is a natural scenario. You consider the worst case or the upper bound. But you know that if you have algorithms that run on linear time complexity of n as an upper bound, it's also upper bound of it is n squared, because it's belong to that family, because order of n is also belong to the n squared. So, but we are looking the tightest upper bound, as what you saw in the lab test. I asked you in the exam lab test, you have to give me the tightest upper bound. Okay. Now, I would like you to take this opportunity and really take 2 or 3 minutes. This is one of the things, this is one of the objectives of this course, is an API is given to you. Being able to read the API and end up with an implementation of this API is very important. And in the next slides, I will discuss with you how the students from previous year, they read this API and implement this API. This API is designed for a recursive method, and it's clearly mentioned that you should not use the loop inside your implementations. Using the loops will receive no credit. We are targeting here implementation of a recursive algorithm. This is one of the questions on the lab test previous year. So if you have a pencil and paper, please, you can take 2 minutes and try to implement it. If you have any difficulty to understand it, you can raise your hand. I will try to explain it. But I will give you a time to read it by yourself and try to come up with an implementation. I encourage all of you to have pencil and paper and try to solve it, because similar questions you will have on the final. And in the final, we have paper paste we not have in the front of the computer. So Again? No, it's clearly here that n is integer. So it's not double. For this particular examples, n is integer. Yes, and n, there is a precondition that n is greater than or equal to 0. So you will not see n is negative. Okay? And we're not asking you to throw any exception if you have n is negative. So we rely on the client or the user who's going to use this method to provide us with input always positive or equal to 0. Okay? Did anyone finish? Finish? Yes. You. Yes, mod and divide by 10, one of the main operation implementation. You try to write correct everything. Yes, you try your best. I'm not gonna like, if you miss a semicolon, it will be disaster. No, give you 0, no. Okay. So let me just go over the API quickly. So you receive integers. Let's say we have examples here. You can see here we receive 36. So we need to investigate all the digits. So if we receive 36, so 3 is odd. That means 3 squared plus 6 would give us 15. Now 3,550, you have 3 squared, 5 squared plus 5 squared plus 0. Okay. Now you have 6, 0, 6, 0, 6, 0. All of them is even. You don't need to square anything of them. So you need to be able to extract each digit, the ones digit, the tens digit, the thousand digits, and look on these digits. If they are odd, you have to square it. Otherwise, you have to retain it itself. Okay? And as you can see, it's very clearly you should not use the loop. If the loop is seen in your implementation, you will not receive any credit. So let us see one of the students how he is approaching this problem to solve it. This is one of the possible solutions. The title is telling you the possible solutions. But might be next time I will change the title. I say one implementation, and we need to check if this implementation is correct and will end with a really terminated correctly. But this solution is correct in terms of the correctness and is will terminate. You can see here the student is start with n. And if asking if n is less than or equal to 10, then he say, I almost have the base case, or I have the base case, but I have to do a little bit of computation here. I will ask n mod 2. If it's equal to 0, I will retain n. Otherwise, I will retain n times n. So this part represent for him is what? The base case. Because he is receiving one digit. 9, 2, 3, 4, because n is less than 10. Otherwise, he will start using the approach that one of you suggested is take integers and convert it to the string and try to extract one element at a time and each recursive call. So he is converting things to the string. So integer dot to string, and you give n, retain a string of I. Now he's starting from the last digits by giving I to substring. Okay, take substring of that I. Then check if n divided by 2. This is the mod operation, is independent from I. Okay, this is related to the n. He starts looking at the n. You see here, what he is doing is retaining n divided by 2. But he is doing this to extract only the digits. He's only using this method to extract the digits. Unfortunately, I was not planning to see such kind of implementations where the string is used. Next version of the exam, I revise it. I say the students should not use the string, because you can solve this without using the string. As you can see, even he did the recursive call n divided by 10. n divided by 10, which is really remove the ones digits. And if you start, let's say, 128, if you divide it by 10, integer division, you will end up with 12 because you got rid of 8, the last one. And this will make sure you check that if the integer is odd or even. I think he's the default implementation. I think this will retain part of the string. Because there is a... Yes. His implementation is correct because this will retain the last digit. Okay, you can try it. If you are not satisfied with, you can take this implementation from this slide, put it in the computer, and try to play with it and see what is retained. Okay. This is another implementation. You can see here the student is asking if I have n is equal to 0, that means I have the base case, I will retain 0. Otherwise, I will try to have integer, he defined integer a is equal to n mod 10, which is retained the remainders, okay, remainder of this divisions, and then define I is equal to 0. After that, he will ask if a it's even or odd. Then he set a to be n divided by 10, which is again different from a here. You have to be careful. Here is putting a is equal to the mod, checking it, then set I, then reset a, and he did recursive call after he said I with a. Okay, that's one of the implementations. There is a redundant in this code. Okay, but still it's work because the component of a recursive algorithm is exist. The base case, at least one base case, and the recursive call. And each time you do the recursive call, you have to go toward the base case. If you're not doing this, you will end up with broken implementation or infinite recursion. Okay? Yes? Yes, indirect recursion. Yes, yes, yes. That is the helper method, is the recursive method. But the main method is calling, we call it indirect recursions. So the main method that is calling the helper method, there is no recursive. This is not a recursive method. The helper method is the recursive method, whereas the component of the recursive method should be exist. One base case at least, one recursive call at least, and each time you do the recursive call, you should go toward the base case. Otherwise, the implementation is broken. Maybe you end up with stack overflow or infinite recursions. Okay. This is the third implementation. You can see the base case here is again n less than or equal to 0, and use integer current to take the mod operations, and then put the result is equal to current, and then check the current if it's odd or even. In this case, he's checking if it's odd, then he's retained the result times the result, and if it's not odd, then the result will be equal to the result itself, and we do the recursive call for n divided by 10. Now, how we can prove the correctness of the recursive algorithm? If someone give you this implementation and you ask you to prove the correctness of the recursive algorithms, we test. Test by taking input example is not a proof. You can show its work for this example, it's work for this example, but this is not a proof. Whenever you need to approve something, you need to prove it for any input. Okay? Which is, if you remember in discrete math, we use the proof by inductions, mathematical inductions. So proof by mathematical inductions, let me just remind you what is the mathematical induction is. If you want to remove anything using mathematical inductions, you need to prove the base case, which is something now, trigger something you might similar to recursive method. So in the proof by inductions, we have the base case. We have something we know for sure it's true. In this case, n is equal to 0 or whatever is the base case, we know the solution and we are 100% sure this solution is true in the proof by inductions. Then we assume that the theorem is valid for n. Using this assumption that the theorem or the valid up to n, we try to prove n plus 1, one step added to n. If we are able to do this, we complete proof by inductions. Okay? And there is another version of proof by induction, which is a strong induction. You have to prove everything from 0 up to n, from the base case up to n. But we are only satisfying this course for proof by inductions, normal proof by inductions. You take the base case, you make sure the base case is correct, you assume for n, then you try to prove for n plus 1. So if we look at the recursive methods, any recursive methods will follow the same style to prove the correctness, and also we have to make sure that it terminates correctly. So we have the base case on the recursive algorithm. The recursive algorithm will not be complete if the base case is missing. At least one. We should see at least one base case on the recursive method. And then we take a problem, we divide it into smaller problem, and we solve these smaller problems. Then at the end, we end up with solving the original problem correctly. So let us see. You remember the power method. If I ask you, you can prove this algorithm or this Java code is correct recursive algorithm. You will say, I will follow the proof by inductions. So we can prove it using proof by inductions. We have the base case. What's the base case? A to the power 0 is equal to 1. Is this method retain a to the power 0 is equal to 1? Power of a to the power 0, we check the argument. Yes, it will retain 1. That means we prove the base case. Now, let us assume if this algorithm is correct up to n. So the inductive step, we prove that if we have k, a to the power k is equal to a to the power k. So if we send k and a, this algorithm will retain a to the power k. So this is the inductive step. Now the next step is to prove for k plus 1. We assume it's correct. We assume it's correct. You should be sure that the base step is correct. You have to make sure that if you send the argument that will end up on the base case, this will correct. In this case, if I send integer x is equal to a and integer y is equal to 0, is this method will retain x to the power y is equal to 0 will retain 1. Is this method do this? Yes. So the base case is correct. We assume the method is correct up to k. Okay? Up to k. Now we need to prove up to k plus 1. To prove up to k plus 1, we look at the method. If we have x is equal to a and y is equal to k plus 1, we end up with what? A times power of a to the k. There is a typo here. This is supposed to be power, P-O-U-W. So a, k. Now the solution for power of a, k, we know it because we assume it on the previous step. The solution for this is a to the power k, which is exactly a to the power k plus 1, which is the correct solution. We prove that this method is correct. Okay? Any question? Yes, if we send a, x is equal to a as an argument. So if any question or someone asks you to prove any recursive algorithms, you're going to use the inductive proof by induction to solve this. Okay? You're going to look at the base case, make sure the base case is correct, assume the inductive step, then prove n plus 1. This is another example we gave last year. We asked the students to do the implementation and return it true if and only if the decimal representation for n has 5 in it. So you can see here, if we have 445, 5 is there on the decimal representation, so we return true. If we have 12,545, 5 is there on the representation, we return true. Now if we receive 128, there's no 5 on the decimal representations. And in this case, we have to return false. Now, if n is equal to 3, which is 1 digit, also 3 does not contain any 5 on the decimal representation, we return false. If you'd like, you can give you 2 minutes. Try to implement this. Use the knowledge that we have on the previous example, how we can isolate each digit and how we reduce the size of the problem from, let's say you receive a number of 6 digits, and how you reduce the recursive call to 5 digits. Okay? You need to divide and you need to take the mod operation. Exactly. You don't need to check everything. So once you see 5 on the decimal representation, you should stop. Just retain, yeah, retain true. That's what we do. Yes. You don't need to look all of them. Okay. So this is one of the implementation from the students. This is a solution from the students. So you can see here the base case is take n divided by 10. Is if it's equal to 0, then he's going to check n is equal to 5, okay? And that means he is receiving integer n with 1 digit. If n divided by 10 is equal to 0, that means integer with 1 digit. If this digit is equal to 5, I'm going to return it true, otherwise I will return false. Again, the same student, you think that it's the same students who did the first implementation, because he is always converting the integers to string. So he convert the integer to string and retain the last value, and if check if the last value is equal to 5, going to return it true. Otherwise, he's going to retain with n divided by 10, reduce the integers by removing the ones digits. So he has 2 base cases and 1 recursive. Another implementation is immediately if n is less than or equal to 0, I'm going to return false. I have a negative because the precondition is saying that only greater than or equal to 0. Now I take the mod operations. If the mod operation is equal to 5, I will return it true. Otherwise, I will call with n divided by 10. So you can see the power here is dividing by 10 here reduce the number of digits on n. If you start with the number of digits 4, then the n divided by 10 will end up with number of digits 3. Because let's say you have 128, you divide it by 10, you end up with 12. So 3 digits to 2 digits. And keep doing this until you have the base case. Another implementation here, you can see if n is equal to 0, we're going to retain false. Then if we have a is equal to divide, I is equal to the mod. If I is equal to 5, I'm going to retain. Otherwise, I will define P as a Boolean of A. Then at the end, I will retain P. Okay. This is another also questions. We ask the students to read this ABI and give us the recursive implementations. And you can see here that we ask from decimal to octets. And you are familiar with this implementation because we discussed last time. So if you receive 9, you retain 1, 1. Okay? 8 is retain 1, 0. And n is equal to 88, you retain 130, which is the actual, the octal representation of the decimal numbers. So you just change the base. In the decimal, you have 10 to the power. Here you have 8 to the power. This is one of the implementations. You take n is less than 0, you retain. There is nothing to represent. If you have n divided by 8 is greater than 8, you're going to call the decimal to octal representation. Else, you're going to print the digits, and then you're going to print the mod operations. So this is the base, and this is the recursive call. This is also another implementations. You can see, I will leave this for you to discuss, to take this implementation and put it inside the Java and really play with it and see how it will give you the correct answer due to the time constraint. Okay, this is a question we ask the students to has only the decimal digit of 5. It's the same version of the previous one, but in this case, you have to check all the digits. You should not stop once you see digit of 5. You have to keep checking that you always see 5 on the decimal representations. So if you have 55, you retain true, but if you have 125, you should retain false, because the representation contains digits that is not equal to 5. The one implementation will be if n is equal to 0, you retain true. Otherwise, you check if the mod operation is not equal to 5, you're going to retain false. Otherwise, you're going to do the recursive code. So you have 2 base cases and 1 recursive code. You can see here is the difference between this implementation and the previous implementation. Is there any wrong on this implementation? Yes. Yes. We need to make sure, look at the ABI, we need to make sure that all the digits are 5. So once we see a digit is not equal to 5, we're going to retain what? False. Now, what's wrong in this implementation? We're going to retain but in terms of the recursive method, all the component is there, the base case is there, recursive code, but the correctness of the algorithm is not correct. Now, this is another implementation. You can see is checking if the mod operation based on 5 is not equal to 0, we're going to retain false. Otherwise, we're going to check if n is less than 10 and n is equal to 5. We're going to retain true. Otherwise, we're going to do the recursive code. So you have 2 base cases and 1 recursive code. Okay. We'll stop right here. Next lectures, we will discuss one more interesting algorithms about recursion, and we close the topic. And we will review some topics from previous lectures. And if you have any questions, we can answer your questions. So most likely next lecture, April 2nd, will be more discussion and answering questions if you have any questions. I hope you start implement the lab test number 6, okay? So because Monday, the last time you're going to see the TA. So if you have any questions,